And now in this lecture I will answer two questions. In the first question we find out the area of this green shape, and in the second question we find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So we start with the first question. In the drawing we have a semicircle. Inside the semicircle we have this small circle. In addition, you know that this is line segment AQ that is equals to 4 units in its length. This is angle AQP that is a right angle. This is angle STB that is also a right angle. It is given us the question that the small line segment TB is equals to 1 unit in its length. Again, our task is to find out the area of this green shape. So first of all, we will define the radius of the big semicircle as x. And the radius of the small circle is y. In the next step, we will define the center of this circle. This point is point O, and we will define the center of the big semicircle. This point is point C. If the radius of the semicircle is equal to x unit in its length, it means that the diameter of the semicircle must be equal to 2x. That is to say, the diameter AB of the semicircle is equal to 2x units in its length. AB equals to 2x units. We define the point of tendency of tangent AB with this small circle. This point is point N. We define the point of tendency of tangent ST with this small circle. This point is point N. We define the point of tendency of tangent PQ with this small circle. This point is point H. Finally, we define the touching point between the semicircle and the big between the small circle and the big semicircle. This point is point K. In the next step, we will join points O and N together by a straight line. Point O is the center of the small circle, point N is the point on the small circle itself, therefore ON is the radius of this small circle that equals to y according to our definition. The radius ON that equals to y, the radius of n is 1 to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and N together by a straight line. OL is of course the radius of this small circle that is equals to y. Again, the radius OL that is equals to y, the radius OL is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever your radius is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the sum rule, rule 1. This gives us the question that this is angle STB, that is a right angle. AB is the diameter of this semicircle, and therefore it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point T, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So each angle we have at the upper side of the straight line AB at point T, we have this angle that is a right angle plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So if we found out that in quadrilateral OLTN, in this quadrilateral OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OLTN, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle in front of a square. So relate to the small quadrilateral OLTN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OLTN, side OL must be equal to the opposite side TN. But OL is y, therefore the opposite side TN must be also equal to y units in its length. In the next step, we join points O and H together by a straight line. OH is of course the radius of this circle that is equal to y. The radius OH is that is equal to y. The radius OH is drawn to point H, that is the point of tendency of tangent PO with this small circle. And whenever your radius that is drawn to the point of tendency, then tangent PO, tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the sum rule, rule 1. And it is given in the question that this is angle PQA that equals to 90 degrees in its size. So if you focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line AB at point Q? We have this angle that is a right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So actually inside the small quadrilateral OHQM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral HONQ, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle in front of a square. So we relate to quadrilateral HONQ as a rectangle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So rectangle HONQ, side HO must be equal to the opposite side QN. But HO equals to y, therefore the opposite side QN must be also equal to y units in its length. Qn equals to y units in its length. So what is the length of line segment QT? QT in total equals to y plus y, that is 2y. QT equals to 2y units in its length. Actually, QT is definitely a straight line because it is part of the diameter AB. AB is the diameter, it is absolutely a straight line, and QT is part of the straight line AB. A part of a straight line must be also a straight line. So QT is a straight line, and therefore QT in total equals to y plus y, that is 2y. So we know that AB equals to 2x, that is the diameter of the big semicircle. And it is equals to AQ plus QT plus TB. Okay, again, from the drawing, it is very easy to see that AB equals to 2x, it is the diameter of the semicircle, and it is equals to AQ plus QT plus TB. So 2x in total equals to AQ is equals to 4 units in its length, plus QT. We just found out that QT equals to 2y. Actually, it is the diameter of the small circle, plus TB. TB equals to 1. So in total, we found out that 2x equals to 4 plus 1 plus 2y. So 2x equals to 4 plus 1 is 5 plus 2y. So 2x equals to 5 plus 2y. Here we will subtract 2y from this equation, and we get that 2x minus 2y equals to 5. Here we'll take 2 out as a common factor from those two expressions. So inside the brackets we left with x minus y equals to 5. So 2 times x minus y equals to 5. Here we will divide this equation by 2, and finally get that x minus y equals to 5 over 2. 5 over 2 is 2.5. So in total we found out that x minus y equals to 2.5 units in its length. What is the length of this missing line segment? Line segment CN. From the drawing it is very easy to see that CN in total equals to CB minus NT minus TB. Again, CN in total equals to CB minus NT minus 2B. So write it down. CN equals to CB minus NT minus TB. And again, you can find out that the length of the short line segment CN is equals to CB minus NT minus TB. CN equals to CB. CB starts from point C, that is the center of the semicircle, and ends at point B, that is the point of the semicircle itself. Therefore, CB is the radius of the semicircle, that is equals to x. Minus nt. Nt equals to y minus tb. tb equals to 1. So in total, if we found out that Cn equals to x minus y minus 1. We already found out that x minus y equals to 2.5. So we substitute x minus y in this equation by 2.5, and you get that Cn equals to x minus y, that is 2.5 minus 1. 2.5 minus 1 is 1.5. So if you found out that the length of the short line 7 Cn is equal to 1.5 units in its length. Cn equals to 1.5. This is the short line 7 Cn. This is equals to 1.5 units in its length. Here we can implement rule 9. Why? Because we have an internal mass between the small circle and the big semicircle. That is to say, they touch each other internally at this point, point K. Whenever you have an internal mass between two circles or semicircles, you can implement rule 9. So I click quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. So in the drawing, we have, this is the big circle, this is the small circle, point O is the center of the big circle, point M is the center of this small circle. The straight line that connects the centers together is, of course, the straight line OM. This straight line OM, according to this rule 9, must pass through point P, that is their touching point. I repeat again, the straight line OM must pass through point P, that is their touching point. OMP is one straight line. Again, OMP is one straight line according to this rule 9. So we can actually implement rule 9 in our drawing. In our drawing, we have an internal mass between the small circle and the big semicircle. That is to say, they touch each other internally at this point K. The center of the big semicircle is here at point C. The center of this small circle is here at point O. The straight line that connects their centers together is, of course, the straight line CO. So the straight line CO, according to rule 9, must pass to point K, that is their touching point. Again, the straight line CO that connects their centers together must pass for their touching point, that is actually point K. Or COK is one straight line. Again, according to rule 9, COK is one straight line. COK, line 7 COK is one straight line according to rule 9. What is the definition of line 7 CK? Line 7 CK starts from point C, that is the center of the semicircle, and then at point K, that is the point of the semicircle itself. This is exactly the definition of a radius. Therefore, CK is the radius of this semicircle, that is equals to X. Likewise, OK is the radius of this small circle, that is equals to Y. So, CO, from the domain, it is very easy to see that CO equals to CK minus OK. Again, CK minus OK equals to CO. CO equals to CK minus OK. So CO in total equals to ck that is x, it is the radius of the semicircle that is x, minus ok that is y. It is the radius of the circle that is y. So in total, we actually found out that CO equals to x minus y units in its length. The short answer at CO equals to x minus y, but we have only found out that x minus y equals to 2.5. So can I know that CO equals to 2.5 units in its length. So in the next step, I'll copy the right triangle OCN in a new project. We will implement on this right triangle OCN the Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the progression for Pythagoras theorem. Side ON equals to y units in its length. Side CN equals to 1.5 units in its length. And the hypotenuse OC equals to x minus y, that is 2.5 units in its length. So actually, this is the right triangle CON that I copied from the original drawing. This right triangle CON, CO squared, that is the square of the hypotenuse, equals to ON squared plus CN squared. So I write it down. CO squared, that is the square of the hypotenuse, equals to ON squared plus CN squared. CO, the hypotenuse CO equals to 2.5 units in its length, therefore CO squared is 2.5 squared, that is 6.25, and it is equals to ON squared. ON is y, therefore ON squared is y squared plus CN squared. CN equals to 1.5 units in its length, therefore CN squared is 1.5 squared, that is 2.25. So in total we found out that 6.25 equals to y squared plus 2.25. Here we will subtract 2.25 from this equation, and we get that y squared equals to 6.25 times 2.25 is 4, so y squared equals to 4. Here we take a root out of this equation, and we get that y equals to the square root of 4, that is 2. So we found out that the radius of the small circle, y equals to 2 units in its length. The radius of this small circle is equals to 2 units in its length. Our task is to find out the area of this green shape. But before that, we'll find out the radius of the big semicircle that is equals to x. We have already found out that x minus y equals to 2.5. But y is 2, so x minus y, that is 2, equals to 2.5. So x minus 2 equals to 2.5. Here we add 2 to this equation, and we get that x equals to 2.5 plus 2 is 4.5. That's actually 9 over 2 units. So she found out that the radius x of the big semicircle is equals to 4.5 units in its length, when the radius of the small circle, y equals to 2. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it's very easy to see that the area of the green shape equals to the area of the semicircle minus the area of the small circle. And again, the area of the green shape is equal to the area of the semicircle minus the area of the circle. So what is the area of the semicircle? The area of the semicircle must be equal to pi times the radius of the circle squared divided by 2. The radius of the semicircle is x, therefore it is pi x squared over 2. So the area of the semicircle must be equal to pi x squared over 2 minus the area of the small circle. The area of the small circle must be equal to pi y squared. Pi times the radius of the circle squared, that is pi y squared. So in total, we found out that the area of the green shape equals to pi times x squared. X is 9 over 2, therefore x squared is 9 over 2 squared minus pi y squared. Y is 2, therefore y squared is 2 squared, it is 4. So in total, this expression equals to 4 pi. We'll open the brackets here and we get that the area of the green shape in total equals to pi times 9 over 2 squared. 9 over 2 squared equals to 9 squared, that is 81, over 2 squared, that is 4. So in total, we found out that there are here the area of the semicircle equals to pi x squared over 2. So it is pi x squared over 2. So it is pi times 81 times 4, that is 9 over 2 squared divided by 2. So in total, the area of the semicircle equals to pi 81 pi over 2 times 4, that is 8. The area of the semicircle equals to 81 pi over 8. We have here minus the area of the circle, that is minus 4 pi. Here we will multiply minus 4 pi by 8 and then we will divide it by 8 in order to have a common factor of this expression, and we get that minus 4 pi times 8 is minus 32 pi over 8. And 81 pi minus 32 pi equals to 49 pi over 8. 49 pi over 8 is 19.24 square units in its size. So repeat again, if we found out that the area of this green shape, that is the area that we are looking for in this question, is equals to either 49 pi over 8 square units in its size, or in terms of numbers, the area of this green shape equals to 19.24 square units in its size. So we finish with the first question. In the next step, I present to you the second question, and we will solve the second question of this lecture. In the second question, our task is to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So in the drawing, you have a semicircle. We know that this is line segment OS, that is equals to 2 units in its length. This is line segment ASB, that is equals to 1 unit in its length. This is angle PQS, that is a right angle. This is angle PTS, that is also a right angle, and we also know that PT equals to TS. Again, our task is to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So first of all, we will complete the semicircle to a circle. So completed the semicircle to a circle, and we will extend 970s by straight line until it touches the circle. We define the touching point of the extended 970s with this circle. This point is point M. In the next step, we will join points N and P together by straight line. By joining points N and P, we get the perpendicular PTN. This is perpendicular PTN. Perpendicular PTN subtend on chord PN. Again, perpendicular PTN subtend on chord PN. So here you can implement rule 5. Repeat quickly on rule 5. According to rule 5, any peripheral angle is equal to 90 degrees must subtend on the diameter of the circle. In the drawing we have a circle. This is peripheral angle MAN, that is a right angle. And therefore, according to this rule 5, peripheral angle MAN must be equal to 90 degrees in its side. And this is peripheral angle MAN, that is a right angle. And according to this rule 5, peripheral angle MAN must subtend on MN, that is the diameter of this circle. And indeed, peripheral angle MAN, that is a right angle, subtend on MN, that is the diameter of this circle. So according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. We can implement rule 5 in our drawing. Why? Because in our drawing, this is peripheral angle PTN. That according to what is given to the question, this is equal to 90 degrees in size. And therefore, according to rule 5, peripheral angle PTN must subtend on the diameter of the circle. Peripheral angle PTN subtend on PN, and therefore, according to rule 5, PN must be the diameter of the circle. So I did know if we found out that according to rule 5, PN is the diameter of the circle. It is given us the question that point O is the center of the circle. Point O is the center of the circle, point P is the point of the circle itself, therefore OP must be the radius of the circle. OB is also the radius of the circle. But OB equals to 2 plus 1. That is to say, the radius of this circle equals to 3. So PO, that is the radius of the circle, must be equal to 3 units in its length. And ON is also the radius of the circle, therefore it is equal to 3 units in its length. Those two angles are defined as vertex angles, so we know that vertex angles are equal to each other. So we define the size of this angle as alpha. And then the size of this angle must be also equal to alpha because they are equal to each other. In the next step, we will do a construction, that is to say, from this point S, we will go perpendicular on ON. From point S, we will go perpendicular on ON. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and ON. This point is point K. So, in the next step, we have here in the right small triangle ONS, OKS, this right small triangle, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the upper right angle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. So it is very easy to see that the right angle PQO is similar to the small right angle QSO according to angle similarity rule. And from the fact that those two right angles are similar to each other, so I prove anyway why the right angle PQO is similar to this right small triangle SQO. First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we can prove that all the triangles of the right angle PQO are correspondingly equal to all the triangles of this right angle OKS, and therefore those two right angles are similar to each other according to angle similarity rule. So write it down. Let me find out that the right angle PQO is similar to the right angle OKS, the small right angle OKS, according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side KS on the small right angle OKS over side PQ of the right triangle PQS is equal to side OS of the right triangle OSK over side PO of the right triangle PQO. Okay, again, from the fact that the right triangle PQO is similar to right small triangle OKS, we know that the following relationship exists between their sides. We know that side KS on the small right triangle OKS over side PQ of the upper right triangle PQS on the upper right triangle PQO is equal to side OS of the small right triangle OKS over side PO of the upper right triangle PQO. KS is the missing side, so we'll leave it as it is. over PQ. PQ is the line segment that we're looking for in this question. It is equals to X. And it is equals to OS, according to what is given to the question. OS equals to 2 units in its length over PO. We already found out that PO is the radius of the circle that equals to 3 units in its length. So in total, we found out that Ks over X equals to 2/3. Again, Ks over X equals to 2/3. Here we multiply this equation by X and finally get that Ks equals to 2/3 X. Again, Ks equals to 2/3 X. In the next step, we define this angle as beta, and we focus on the big right angle PTN. On the big right angle PTN, this angle equals to beta, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta. 1 equals 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in an angle. Likewise, in this small green triangle KSN, this angle equals to beta. Actually, angle beta is a common angle that belongs to both triangles. So this angle equals to beta, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta. Actually, it is very easy to see that the big right triangle PTN is similar to this small green right triangle KSN. I'll prove anyway why the big right triangle PTN is similar to this small right triangle KSN. First of all, this is angle beta. That is a common angle that belongs to both triangles. So we can write out that angle beta equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees minus beta, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So we found out that all the figures of this big right triangle PTN are corresponding equal to all the figures of this small green triangle KSN. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down, and we found out that the right big triangle PTN, this is the right big triangle PTN, is similar, this is the sign of similar, to the right small green triangle KSN, according to angle similarity rule. And from the fact that the right triangle PTN is similar to the right green small triangle KSN, we will derive that the following relationship exists between their sides. We will derive that side KS of the small right triangle KSN over side PT of the big right triangle PTN is equal to side SN of the small right triangle KSN over side PN of the big right triangle PTN. Again, from the fact that the big right triangle PTN is similar to the small right triangle KSN, we will derive that the following relationship exists between their sides. We will derive that side Ks of the small right triangle KSN over side PT of the big right triangle PTN is equal to side SN of the small right triangle KSN over PN or side PN of the big right triangle PTN. Ks, we already found out that Ks equals to 2/3 x over PT. We know that PT equals to TS. According to what is given in the question, PT equals to TS. So we define the length of PT as A, and therefore TS must be also equal to A because they are equal to each other. So PT is A according to our definition. And it is equal to SN. What is the length of SN? SN is the missing side, so we leave it as it is. So it is SN over PN. What is the length of PN? PN, actually it is the diameter of the circle. The radius is 3, therefore the diameter must be equal to 6. So PN equals to 3 plus 3, that is 6. Is the diameter of the circle. So in total we found out that 2/3 x over A equals to Sn over 6. Here we cross multiply this equation, and finally we get that 2/3 x times 6 equals to ASN. And again if we found out that 2/3 x times 6 equals to ASN. Six over 3 is 2, and therefore in total this expression equals to 2 times 2x, that is 4x. So in this of those equation we have 4x equals to ASN. This will be equation 1. So according to equation 1, 4x equals to ASN. So here we can implement rule 15. Please click on rule 15. According to rule 15, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. So in the drawing we have a circle. In this circle we have chord AB that intersects with chord CD at point O. Point O is the intersection point between chord AB and chord CD. So in this drawing the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 15 in our drawing. Because in our drawing we have chord TN that intersects with chord AB at point S. Again, chord TN intersects with chord AB at point S. So write it down. Now drawing. Chord TN intersects with chord AB and the intersection point occurs at this point, point S. This is point S. This letter is S. So chord at Tn intersects with chord AB at point S. And therefore, according to rule 15, the following equation will be true. That Ts times Sn is equal to As times Sb. It again. Now drawing chord Tn intersects with chord AB at point S. And therefore, according to rule 15, Ts times Sn equals to As times Sb. This equation is the implementation of rule 15 in our drawing. Ts, this is line 7 Ts, that equals to A units in its length according to our definition. This letter is A. So Ts is A times Sn. Sn is the missing side, so we leave it as it is. So it is A times Sn. A times Sn is equal to As times Sb. As in total equals to AO plus OS. That is to say, As equals to AO, that is the radius of the circle, that is 3, plus OS, that is 2, according to what is given us the question. So in total, AS equals to 3 plus 2, that is 5. AS equals to 5 times SB. SB equals to 1 unit in its length, according to what is given us the question. So in total, we shall find out that, according to rule 15, A times Sn equals to 5 times 1, that is 5. So if we found out that, according to equation 2, A times Sn is equal to 5. This is according to equation 2. Well, according to equation 1, A times Sn is equal to 4x. So in the next step, we get equation 3 that says that A times Sn, according to equation 1, must be equal to A times Sn according to equation 2. So A times Sn according to equation 1 is equal to 4x, and it must be equal to A times Sn according to equation 2. A times Sn according to equation 2 is 5. So in total, according to equation 3, we found out that 4x equals to 5. So here we will divide this equation 3 by 4, and finally we get that x equals to 5 over 4. 5 over 4 is 2.25 units. So if you found out that the line segment that we are looking for this question, that is actually line segment PQ, line segment PQ, that is equals to x, is equals to either 5 over 4, so units in its length, or in terms of numbers, the length of this short line segment PQ that is equals to x is equal to 1.25 units in its length. So we finish with the second question. In the next step, I will summarize the lecture. I'll start with the first question, of course. In the first question, our task was to find out the area of this green shape. So in the drawing we have a circle inside the big semicircle. We know that 978 AQ equals to 4 units in itself. This is 917 bit is equals to 1 unit in itself. This is angle PQA, that is the right angle. This is angle STB, that is also a right angle. And our task is to find out the area of this green shape. So first of all, we define the center, we define the radius of this big semicircle as x, and we define the radius of this small circle as y. We define the center of this small circle, this point as point O, and we define the center of this big semicircle, this point as point C. AB is the diameter of the semicircle, the radius is x, therefore the diameter must be equal to 2x. So AB equals to 2x. So AB equals to AQ plus QT plus TB. So in the next step we join points, we define the point of tendency of tangent AB with this small circle, this point is point N. Likewise, we define the point of tendency of tangent PQ with this small circle, this point is point N. We define the point of tendency of tangent ST with this small circle, this point is point N. And finally, we define the touching point of the small circle with the big semicircle, this point is point K. So we join points O and N together by side line. Point O is the center of the small circle, point N is the point of the small circle itself, therefore ON is the radius of this small circle, that is equals to y according to our definition. ON equals to y. The radius ON, that is equals to y, the radius ON is 1 to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. We know that according to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. AB is the diameter of this semicircle, therefore it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point Q? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We join points O and H together by straight line. OH is of course the radius of this circle, that is equals to y. The radius OH is equals to y. The radius OH is 1 to point H, that is the point of tendency of tangent PQ with this small circle. And whenever your radius is 1 to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside the small quadrilateral HO and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 missing angle, in total it must be equal to 360 degrees. According to the rule, the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 missing angle must be equal to 90 degrees in its size. So inside quadrilateral O and Q, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at this rectangle and not a square. So remember to this quadrilateral NO edge Q is rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle AO and Q side AO must be equal to the opposite side QN. But AO is y, therefore the opposite side QN must be also equal to y units in its length. Repeat it with the same process. Here, we join points O and N together by straight line. OL is the radius of the circle that equals to y. The radius of L is drawn for point L. This is the point of tendency of tangent Sn of tangent St with this circle. And whenever your radius is drawn to the point of tendency, then tangent St will be perpendicular to the radius LO. If S is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the same rule 1. Here, this angle equals to 90 degrees in its size, according to what is given in the question. So if you focus on the upper side of the straight line AB at point T, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have the upper side of AB at point T? We have this angle that is right angle, plus this facing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this facing angle must be equal to 90 degrees in its size. So in size quadrangle OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 facing angle must be equal to 90 degrees in its size. So in size quadrangle ONTN, we have 4 right angles. And according to rule 5, in quadrangle that has 4 right angles must be this rectangle plus a square. So we know to quadrangle ONTN is rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle ONTN, side OL must be equal to the opposite side NT. But OL is y, therefore the opposite side NT must be also equal to y units in its length. So QT, line segment QT, is a straight line because it is part of the straight line AB. A part of the straight line must be also a straight line. So QT is a straight line. So QT in total must be equal to y plus y, that is 2y. So QT equals to 2y. So what is the length of the, know that AB equals to 2x. AB equals to 2x, and it is equals to AQ, that is 4, plus QT, that is 2y, plus TB, that is 1. So if you found out that AB is equals to 2x equals to AQ, that is 4, plus QT, that is 2y, plus TB, that is 1. So in total 2x equals to 4 plus 1, that is 5, plus 2y. So 2x equals to 5 plus 2y. Here we subtract 2y from this equation and find out that 2x plus 2y equals to 5. Here we took 2 out of this equation. It's a common factor, so inside the brackets we left with x minus y. So 2x minus y equals to 5. Here we divided this equation by 2 and find out that x minus y equals to 5 over 2, that is 2.5. So x minus y equals to 2.5 units in its length. What is the length of this missing line segment CN? From the drawing it is very easy to see that CN in total equals to CB minus NT minus TB. Again, CN equals to CB minus NT minus TB. And again, if you found out that CN in total equals to CB minus NT minus TB. So CN equals to CB. CB is the radius of the semicircle that is x, minus NT. NT is y, minus TB is 1. And CB is x, NT is y, and TB is 1. So in total, CN equals to x minus y minus 1. So CN equals to x minus y. X minus y is 2.5. So we substitute x minus y by 2.5 minus 1. 2.5 minus 1 is 1.5. So in total, we found out that CN equals to 1.5 units in its length. This is the length of this short line segment CN is equal to 1.5 units in its length. So here we can implement rule 9 because we have an internal knot between the semicircle and the small circle. That is to say, they touch each other internally at this point K. So we can implement here rule 9. We can click on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes for their touching points. So in the drawing, we have a big circle with the center of O. The center of this small circle is at point M. The straight line that connects the centers together is of course the straight line OM. And according to this whole line, the straight line OM must pass for their touching point, that is point P. Again, the straight line OM must pass for point P, that is their touching point. Or O and P is one straight line. Again, O and P is one straight line. So we can implement whole line in our drawing. In our drawing, we have an internal notch between the big semicircle and the small circle. This is to say they touch each other internally in this point K. The center of the big semicircle is at point C. The center of this small circle is at point O. And the straight line that connects the centers together is the straight line CO. And according to our line, the straight line CO must pass for point K. That is their touching point. Again, the straight line CO must pass for their touching point, that is point K. Or COK is one straight line. Again, COK is one straight line. Again, COK is one straight line according to all 9. If COK is one straight line, it means that CO must be equal to CK minus K. Again, CO must be equal to CK minus K. So CO equals to CK equals to CK equals CO. This is the missing side CO equals to CK minus OK. So CO, this is the missing side CO equals to CK. Point C is the center of the semicircle, point K is the point of the semicircle itself, therefore CK is the radius of the semicircle, this is equals to X. So CK equals to X minus OK. OK is the radius of the circle, that is Y. OK equals to Y. So in total, CO equals to X minus Y. This is the missing side CO, that equals to X minus Y. But we already found out that X minus Y equals to 2.5. So can I down here that X minus Y, that the length of the hypotenuse CO is 2.5. In the next step, I copied the right triangle CON in your page and implemented the Pythagoras theorem on this right triangle CON. According to the Pythagoras theorem in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle CON that I call it from the original drawing. In this right triangle CON, CO squared, that is the square of the hypotenuse, equals to ON squared plus CN squared. CO is 2.5, therefore CO squared is 2.5 squared, that is 6.25, and it is equals to ON squared. ON is Y, therefore ON squared is Y squared plus CN squared. CN is 1.5, therefore CN squared is 1.5 squared, that is 2.25. So in total, we found out that 6.25 equals to Y squared plus 2.25. Here we subtract 2.25 from this equation, and we found out that Y squared equals to 6.25 plus 2.25 is 4. So Y squared equals to 4. Here we took out of this equation, and we found out that Y equals to the square root of 4, that is 2. So if we found out that the radius of this small circle Y equals to 2 units instead. We already found out that X minus Y equals to 2.5. Y is 2. So X minus Y is X minus 2, that is equals to 2.5. So X minus 2 equals to 2.5. Here we added 2 to this equation, and finally found out that X equals to 2 plus 2.5 is 4.5. 4.5 is 9 over 2. So if you found out that the radius of this big semicircle, X equals to 4.5 or 9 over 2 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of the semicircle minus the area of the circle. Again, the area of the green shape equals to the area of the semicircle minus the area of the circle. The area of the semicircle equals to the area of the circle over 2. The area of the circle is pi x squared over 2. So the area of the semicircle in total equals to pi x squared over 2. Minus the area of the small circle, that is pi y squared. X is 9 over 2, therefore x squared is 9 over 2 squared. So pi x squared over 2 is pi times 9 over 2 squared over 2. Minus y is 2, so y squared is 2 squared, that is 4, so pi y squared is 4 pi. Here we open the brackets and found out that actually that 9 over 2 squared equals to 9 squared, that is 81, over 2 squared, that is 4. So in total, this expression equals to 81 pi over 2 times 4 minus 4 pi. Here we multiplied 4 pi by 8 and then we divided by 8 in order to become factor with this expression. And we found out that minus 4 pi times 8 is minus 32 pi. So in total, we found out that the area of the ratio equals to 81 pi minus 32 pi over 2 times 4 is 8. 81 pi minus 32 pi is 49 pi over 8. So if you found out that the area of this range shape equals to either 49 pi over 8 square units in size, or in terms of numbers, the area of this range shape equals to 19.24 square units in its size. So we finish with the first question. In the next step I presented you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So in the drawing, we have a semicircle. We know that this is line segment OS that is equals to 2 units in its length. This is line segment SB that is equals to 1 unit in its length. We also know that PT equals to TS. This is angle PQ, or that is a right angle. This is angle PTS, that is also a right angle. Again, our task is to find out the length of this short line segment PQ that is equal to x. We have to find out the value of x. So in the first step, we completed the semicircle to a circle, and we extended line segment TS by a straight line until it touches the circle. We define the touching point of the extended line segment TS with the circle. This point is point N. In the next step, we join points N and P together by a straight line. By doing all those constructions, we get the peripheral angle PTN. This is peripheral angle PTN, that is equals to 90 degrees in size. Peripheral angle PTN subtend on chord PN. Again, peripheral angle PTN subtend on chord PN. So here we can implement rule 5. According to rule 5, any peripheral angle that is equals to 90 degrees in size must subtend on the diameter of the circle. Peripheral angle PTN equals to 90 degrees in size, and therefore it must subtend on the diameter of the circle. Peripheral angle PTN subtend on PN, therefore according to rule 5, PN must be the diameter of the circle. Okay, PN is the diameter of the circle. In the next step, we did the construction, that is to say, from this point S, we do perpendicular on PN. Again, from point S, we do perpendicular on PN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle alpha as alpha, then the size of this angle must be also equal to alpha, therefore, because they are equal to each other. So in the right angle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. Likewise, in this small right angle OSK, this angle equals to alpha. This angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha, because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees, that is the sum of the angles in a triangle. So actually, triangle PQO, that triangle PQO is similar to this triangle OSK according to angle similarity rule. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I should found out that all the triangles of the right triangle POQ corresponding equal to all the figures of this right triangle OSK. And therefore, those two right triangles are similar to each other according to angle similar to rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side KS of this one right triangle KSP, of this one right triangle KSO, over side PQ, over side PQ of this right triangle PQO is equals to side PS, side is equal to side OS of this one right triangle SKO over side PO of the right triangle PQO. Again, we found out that KS over PQ equals to OS over PO. KS is the missing side, so it is PQ is X, SO is 2, and PO is 3. So in total, we found out that KX over X equals to 2/3. Here we multiply this equation by X and found out that KS equals to 2/3 X. KS equals to 2/3 X. In the next step, we find this angle as beta. So in the right triangle, the big right triangle PTN, this angle equals to beta, this angle equals to 90 degrees. And therefore this angle must be equal to 90 degrees minus beta. Y equals 90 degrees minus beta plus beta is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small green right triangle SKN, this angle equals to beta. This angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus beta. Okay, so okay, found out that the right triangle PTN is similar to this one green right triangle KSN according to angle similarity rule. That is to say, this is angle beta, that is a common angle that belongs to both triangles. So we can write down that angle beta equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta and therefore they are equal to each other. So we found out that all the figures of this big right triangle PTN are correspondingly equal to all the figures of this small right triangle KSN. And therefore those two right triangles are similar to each other according to angle similar to. So if we found out that the right big triangle PTN is similar, this is the sign of similar to the right small green triangle KSB according to angle similar to rule. And from the fact that the right big triangle PTN is similar to the right green small triangle KSN, we derive that the following relationship exists between their sides. We derive that side KS of the green small right triangle KSN over side PT of the big right triangle PTN is equals to side SN of this small green right triangle KSN over side PN over side PN of the big right triangle PTN. Actually, this is side PN. This is side PN of the big right triangle PTN. Again, we will derive that KS over PT equals to SN over PN. KS, we already found out that KS equals to 2/3 X over PT. PT is A according to our definition, and it is equal to SN. SN is the missing side, so we leave it as it is. Over PN. PN is the diameter of the circle. The radius is 3, therefore the diameter is 6. So PN equals to 6. So in total, we found out that 2/3 X over A equals to NS over 6. SN over 6. Here we cross multiply this equation, and finally found out actually that 2/3 x times 6 equals to ASN. 6 over 3 is 2, and 2 times, so in total, this expression equals to 2 times 2x, that is 4x. So 4x equals to ASN. This is according to equation 1. So if we can implement in our drawing rule 15, I can click on rule 15. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. Again, we have in the domain a circle, and we have chord AB that intersects with chord CD at point O. So in this domain, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 15 in our domain. Why? Because in our domain, we have chord Tn that intersects with chord AB at point S. Again, chord Tn intersects with chord AB at point S. Okay, open again. Now in drawing, we have chord Tn that intersects with chord AB at point S. Chord AB. Again, chord Tn intersects with chord AB at point S. Chord Tn intersects with chord AB at point S. So according to rule 15, Ts times Sn equals to As times Sb. Again, Ts times Sn equals to As times Sb. According to rule 15, Ts times Sn equals to As times Sb. Ts is A times Ns. Ns is the missing side, so we leave it as it is. So in this side of the equation, we have A times Ns, and it is equals to As in total equals to AO, that is 3, plus Sn, that is 2. So in total, A equals to 3 plus 2, that is 5. So AS equals to 5 times SB. SB equals to 1. So in total, if you found out that A times Sn equals to 5 times 1, that is 5. So ASN equals to 5 according to equation 2. Well, according to equation 1, we have found out that ASN equals to 4x. In the next step, we created equation 3 that says that ASN according to equation 1 must be equal to ASN according to equation 2. So again, according to equation 3, ASN according to equation 1 must be equal to ASN according to equation 2. ASN according to equation 1 equals to 4x. And it must be equal to ASN according to equation 2. ASN according to equation 2 equals to 5. So in total, we actually found out that 4x equals to 5. Here we divided this equation by 4 and found out that x equals to 5 quarters, or in terms of numbers, x equals to 1.25. So the length of this line segment PQ that is equals to x is equals to either 5 quarters, in terms of numbers, PQ that is equals to x is equal to 1.25 units in its length. Okay, thank you very much.